Sheet 2 Mechanics Revision. The first problem, a uniform solid cylinder of radius r is placed on a rough horizontal surface and is given a linear velocity VCM equal to 10 meters per second. And angular velocity omega is shown. The cylinder comes to rest after moving some distance to the right. That means the velocity of the center of mass becomes 0, the omega becomes 0 after a while. We need to find omega. Now, this is a very simple stuff on conservation of angular momentum. Realize, start from this state, look at this point of contact. What's the angular momentum about the point of contact in this final state? 0. mvcm into r minus ICM omega, which is 0 in this. That means angular momentum in this state must also be 0. Yes or no? About the point of contact, the angular momentum must have been 0. Whatever state that you imparted to it at this instant of time, the angular momentum here must have been equal to angular momentum here. Why? Because through this point, weight and normal reaction will pass, friction will pass. There is no torque about this point. So angular momentum about the point of contact must remain preserved at all times. And we know the value of the angular momentum at some instant of time. At this instant of time, the angular momentum about the point of contact has been 0. So it must have been 0 to begin with also in this condition. Right? So all that you need to do is angular momentum about the point of contact, in this case 0, must be equal to angular momentum about the point of contact in this case. Realize that because of pure translation, the angular momentum about the point of contact is mvcm into r clockwise, and because of anti-clockwise omega, it's minus ICM omega. That's the net angular momentum about the point of contact, and that must be 0, which is the angular momentum in this state, remaining preserved at all times. And then this gives you an opportunity to compute omega if this is a cylinder. So ICM for a cylinder is half mr squared, etc. And then you can push this. Clear? Now in this case, kinetic energy is not conserved. Obviously it's not conserved because it does not start rolling. So friction, realize that you can't conserve kinetic energy here. To begin with, we had an VCM like this and an omega like this. Look at this point of contact. Its velocity at this point, because of pure translation, VCM, because of omega, it's r omega. Therefore, friction, there is actual sliding, there is rubbing, friction which is mu mg acts like this, right? So, there is relative motion between the body and the surface, and therefore there is loss of energy, and that's the reason, kinetic energy does become 0. It doesn't start with 0 here, it becomes 0 there, right? It's like half mvcm squared plus half ICM omega squared. That obviously can't be 0. Kinetic energy is not conserved because friction eats into the energy. Right? There is sliding, it's not a state of rolling for sure. In a state of rolling, velocity of the point of contact must have been same as the velocity of the surface, in this case 0, which is not the case. right? Had it been a case of rolling, you could have preserved kinetic energy on a horizontal surface, right? Not in. Uniform disk of mass m, is rolling without slipping on a horizontal surface with a velocity v. A particle of mass small m, much less than capital M, gets detached from the point P of the disk at time t equal to 0 when the coordinates of P are 0, 2r, that means from this point. Obviously, one thing, if it's rolling without slipping on a horizontal surface, then the omega must have been like this, right? And that V must have been equal to r omega. The velocity of the point of contact is V minus r omega, which is 0. So V must have been equal to r omega for rolling without slipping on a horizontal surface in the absence of any other force, right? And therefore, the velocity of this point, because of pure translation V, because of pure rotation about the center of mass, r omega, but r omega must have been V. So the velocity of the topmost point must have been equal to 2v, right? So when it gets detached, when it gets detached, then this mass m has a velocity 2v like this and has a 0 velocity like this. The time it takes to fall a height 2r is half gt squared, right? It takes up a parabolic trajectory. In this time t, it covers a distance x, which is 2v into t. It covers the distance x, which is 2v into t. Yes or no? As simple as this. Is that all right? So when it gets detached, it's solely under the influence of gravity. It takes up a parabolic trajectory. The time it takes to get displaced by an amount 2r is going to be given by t. ut plus half gt, u is 0 in the vertical direction, and the horizontal displacement x would be 2v into t, t known from here, etc. Simple. Alright, so we have a smooth inclined plane as shown, fixed, and there is a particle that falls from a height h. The particle that falls from a height h is known to you, and it rebounds from the inclined plane and falls somewhere on the ground, right? We need to figure out how far away from C does it fall, the time it takes to fall through a vertical displacement 1 meter, etc. Now, simple stuff, because look, when it falls, it impinges the plane with a velocity v naught, which is root 2 gh. It impinges the plane with a velocity v naught, which is root 2 gh. This velocity v naught had a horizontal component, and a vertical, a perpendicular component and a component parallel to the plane. That's what I meant. Perpendicular component, perpendicular to the plane, and a component parallel to the plane, right? The component perpendicular to the plane is v naught by root 2, v naught cos 45 degrees, and this would be v naught sin 45 degrees, right? So this is like v naught by root 2 is the parallel component, right? Now, just after the impact, which component will get affected? This normal component. Impact is along the normal direction. The parallel component will remain unaltered. Why? Because there is no friction. So, just after impact, the velocity profiling is as follows. So, component in this direction would be E times V naught by root 2 would be E times V naught by root 2. So, E is 0.8 whatever, I'll just and V naught by root 2 and V naught by root 2. Yes or no? Say this is the x direction and say this is the y direction. So its velocity at this point C in the x direction just after impact its velocity in the x direction at this instant is going to be e v naught by root 2 cos 45 degrees plus v naught by root 2 cos 45 degrees. Yes or no? That will be its horizontal velocity just after impact. Is it not? Its horizontal velocity just after impact would be this cos. See, all these angles are 45 degrees. Right? So its horizontal component of velocity would be this cos 45 degrees, which is EV naught by 2. This cos 45 degrees would be EV naught by 2 plus V naught by 2. V naught by root 2 cos 45 degrees. So V naught by 2. So which is V naught by 2 into E plus 1. Where V naught we know is root 2 GH anyways. Is that alright? And it's, are you there with me on that? And its vertical velocity would be, initial vertical velocity would be V naught by root 2 cos 45 degrees minus EV naught by root 2 sin 45 degrees. Yes or no? That will be its vertical velocity just after impact, right? So V naught by root 2, which is like V naught by 2 minus EV naught by 2, right? This cos. Component of this in this direction minus component of this in this direction would be the downward vertical velocity at just after impact, which is V naught by 2 into 1 minus E. And now it's a case of ordinary projectile motion. You know the horizontal component of the velocity, you know the vertical component of the velocity. In order to go from C to a vertical displacement of 1 meter is desired. So 1 meter of vertical displacement with the initial vertical velocity uy takes place in time t plus half gt squared. You solve t, then you will get the time it takes to go to a, right? If you solve this quadratic in t, this will give you the positive value of time will give you the time it takes to go from C to A, accomplishing a vertical displacement of 1 meter. Yes or no? And then this distance PA would be enabled because ux acts for t seconds. Ux acts for t seconds. Yes or no? So ux acting for t seconds will give you AP. And you know this distance, this is 1 meter, because this is 1 meter. So this will be PA minus 1 meter would be the required distance from the inclined plane. As simple as this. Fair enough? Alright. So when this fellow falls down, it impacts this with a velocity v, which would be root 2 gh. 10, 10, 100. So 10 meters per second. These are two identical balls in a state of perfectly head-on elastic collision. What would they do? They would exchange velocities. So then this guy would come to rest and this would carry the momentum forward. This would move with a velocity of 10 meters per second, right? So just after collision, this leaves the scene and this starts to move with a velocity of 10 meters per second. Right? Now we need to find, I guess, the time in which the frictional force becomes 0, which means time in which perfect pure rolling commences. Yes or no? Right? Time in which pure rolling commences. Now it's given that it's significantly rough, means it doesn't take long for it to have rolling commenced, right? Greater the value of mu, smaller is the time it takes to accomplish pure rolling conditions. We've seen that in the past, right? So whatever be it, realize that at this instant of time, this has a velocity of 10 meters per second to the right. Velocity of this is also 10 meters per second to the right. It has no omega initially. So then frictional force, maximum static acts here, mu mg acts here, right? And therefore causing a retardation of mu g, A retardation of mu g is accomplished because mu mg acts like this, Now, what all would transpire? This mu g would begin to kill this 10 meters per second, right? So when pure rolling starts, let's say V becomes VCM, which would be initial velocity 10 minus mu gt, minus 80, right? Minus mu gt. That's a VCM at the instant of pure rolling. And what does this mu mg do? It produces a torque like this about the center of mass, causes an alpha to develop. What's the angular acceleration? The angular acceleration produced is like the torque about the center of mass, mu mg into r divided by I about the center of mass. It's a cylinder, right? It's a sphere. Is it a sphere? So 2/5 mr squared, right? Right? So you know this, so which is like a 5/2 mu g by r. 5/2 mu g by r radians per second squared is the angular acceleration. Now in t seconds, it would have developed a clockwise angular velocity omega. So in t seconds, it develops an omega. Initial omega is 0, omega is omega naught plus alpha t, where alpha is this. So omega would be alpha into t. That means 5 mu g by 2r into t, right? So now we need to find t given that pure rolling just about commences at this point. That means VCM must be equal to r omega. So 10 minus mu gt must be equal to r omega. R omega is 5 mu g t by 2. So you would know the instant of time. When pure rolling commences. Fair enough? And once pure rolling commences, then the velocity of the point of contact becomes 0. And then I told you on a horizontal surface, once rolling has seeped in and there are no other forces, frictional force is 0, because if frictional force still acts, then it would be deterrent towards rolling condition. It will either disrupt VCM to break the parity VCM equal to r omega, or it will disrupt omega to kill V equal to r omega. In one direction or the other, if it acts, it will disrupt either VCM or omega to kill the compactness VCM equal to r omega, right? So friction will cease to act because it need not act after this. VCM equal to r omega will continue to happen, and frictional force will be dormant. Beyond this point, t seconds, once rolling starts. That is obviously under the condition that there are no other forces acting. If there were other forces acting, then friction will still act, although under rolling conditions, frictional force would be less than maximum static, can have any value from 0 to F max stat, right? That's what would happen. But in this case, static friction is 0 here, right? I hope all of you understand this. So friction will cease to act in t seconds. Friction will cease to act, 10 minus mu gt, etc. Simple. So there is a rod whose center of mass has a velocity 2v0, and the end B is found to have a velocity v0. We need to find the kinetic energy of this rod at this instant of time. Hey, realize that there is an angular speed associated with it. What's the angular speed? V0 by L by 2, yes or no? V0 divided by L by 2. Are you there with me on this? Difference in these two perpendicular velocities divided by this length, that would be the angular velocity, right? So, which is like V0 by L by 2. V0 by L by 2. This length is L by 2. V0 by L by 2. Isn't it? That's the omega for the system. And then once you know the velocity of the center of mass, once you know the omega for the system, then the kinetic energy of the system would be what? Half m VCM squared plus half ICM. What's ICM for this? 1/12 ml squared is the ICM for this. 1/12 ml squared is the ICM for the rod. Clear? Straightforward. Now one thing, even without doing too much hanky-panky, can you tell me whether the spring will be compressed or elongated? Huh? Yes, it will be compressed. Because if you look at the equilibrium of the cylinder, then at this point, there could be only one direction of tension acting. And this tension about the center would produce a clockwise torque, right? And that must be countered by a anti-clockwise torque because of spring force. So spring force must therefore act in this direction. Spring force must act in this direction so that the spring force about O produces an opposing torque, producing no torque about O for the cylinder to maintain equilibrium conditions, right? So for the spring to exert a force in this direction, the spring ought to have been compressed. The spring ought to have been compressed for sure. Are you there with me on this? All right. Now, if I know T, then I can find Fs, and in which case I can find the compression in the spring, which is K. Simple as that. And to know T in the string, I go back to this mass, the equilibrium of this mass, which is subject to three forces. One is tension upwards. The other one is weight downwards. Weight is like, the density of this is 2 sigma. So 2 sigma V into G, that's a weight downwards. And there is an upthrust, which is weight of fluid displaced. The buoyant force, it displaces V cubic meters with density rho. So this is like V sigma G. This is the summary of forces acting on the mass, producing equilibrium on the mass. And therefore, we have like T plus V sigma G equals 2 sigma Vg. So T is known to us. The tension is sigma Vg. Tension is sigma Vg. Once you know the tension, let's say X is the compression in the spring, then Fs will be Kx. The spring force in this direction would be Kx, taking torque about O. T into R, the clockwise torque, must be equal to the anti-clockwise torque, Kx into R by 2. Right? Net torque about O equal to 0, clockwise torque equal to anti-clockwise torque. You have some confusion, na? No. So T we know from those considerations, and X could then be computed. That's simple. Fair enough? You don't want to go through tough times with me towards the fag end, right? Alright, so we have this square lamina, mass m of this lamina, and a particle of mass m with a velocity v strikes the point A, this vertex of the square as shown, and gets involved in a perfectly elastic collision, right? Now we need to figure out what happens just after collision to the lamina and to the particle in terms of the kinematic status of both, right? This in principle is what we are seeking for the problem. Ordinary stuff, because all that you need to do is look at this mass m. Just prior to collision, it had a velocity in this direction, right? At A, this is not at this point, symbolically representing, it had a velocity v cos 45 degrees horizontally and v sin 45 degrees vertically. So then v by root 2 is what it had, impinging normally onto the plane at A, and v by root 2 brushing past the lamina, isn't it? The lamina can be assumed to be smooth, in which case the vertical component of the velocity of the particle m remains the same, right? This component of the velocity would have got altered only if there was friction, because this component is brushing past This way. So it would have responded only to the presence of friction, right? Whereas this is the component at A which is creating an impact, and this is the component participating in the process of collision. The colliding component is this. This is a passive component because there is no friction. Anyways, this is not responsible for any impact. Good now? Okay, so this is the state just before collision, right? And this is sitting neat, doing nothing, zero velocity, zero angular velocity, etc. Right? This is just before collision. Now, what happens just after collision? Look, this creates an impact in this direction. This creates an impact on the lamina in this direction. It exerts an impulse on the lamina in this direction, yes or no? In effect, producing on the lamina, just after impact, VCM is because of the impact along the common normal direction, yes or no? And the impulse that it exerts on the lamina in this direction produces, see, if it's an impulse that it's exerting on the lamina at A, producing on the lamina an angular velocity omega. This angular impulse on the lamina will produce an angular velocity, change in angular momentum, and therefore an angular velocity, yes or no, about the center of mass. So I know this is what is transpiring onto the lamina. There is a VCM produced on the lamina, there is a omega produced on the lamina. There is no velocity in this direction produced on the center of mass, right? Because in this direction, the two mutually agree not to participate, right? This is passive. This doesn't even know that this particle has a vertical velocity because there was no friction, right? So this is the state of the lamina just after collision, right? The particle M after collision. So this is the lamina mass M just after collision. Now, this component of the velocity gets altered for the particle M. Since the particle exerts on the lamina a force in this direction, the lamina exerts on the particle equal and opposite impulse in this direction, thereby altering the velocity in the common normal direction. This is the common normal direction. This is the common normal direction of collision, right? So, at A, just after collision, the particle of mass M has a velocity v1, which has got altered because of the mutual impulses that the lamina and the particle exerted on each other in the common normal direction. But this velocity remains the same for the particle. Now, this is understood, right? This is the structure of the velocities for the particle and the lamina. Now, come to the conservation laws that become relevant to this situation. For the lamina plus the particle, looked upon as one unit, lamina plus the particle, in this direction, let's say the x direction, is there any loss of linear momentum? No, there is no external force acting on the system. So for the particle plus the lamina, the total linear momentum in the x direction before and after collision must be the mass M brought a linear momentum in the x direction to the system, mv by root 2. Right? And then, just after collision, it retained a linear momentum mv1 with itself and shared mvcm with the lamina. Yes or no? That's linear momentum. Along the x direction. Fair enough? Obviously, to simplify matters, this m will get cancelled. Yeah, please ask. No confusion. Now, the angular momentum of the system. This is the linear momentum issue, the angular momentum issue of the system. About what point is the angular momentum of the particle plus system conserved? Or particle plus lamina conserved? Huh? About all points, about all goddamn points, angular momentum is conserved. There is no torque because of an external force about any point in the, right? So you have the freedom and liberty to take angular momentum about any point. I could have taken angular momentum about the center of mass of the lamina, which would be your instinctive reaction to the situation, right? But then a mature reaction to the situation would be to take angular momentum about a point which offers the least amount of dirt and mess, right? I would choose to take angular momentum about A. To begin with, realize that the velocity of M passes through A, so it produces how much angular momentum about A? 0, right? So the system about A just before collision houses 0 angular momentum, houses 0 angular momentum about A just before collision. Yes or no? So I'll take angular momentum about A, which is 0. So to begin with, 0 angular momentum just before collision, and just after collision, the velocity of this still passes through this point. So the particle just before and just after had 0 angular momentum. So then the lamina just after collision, so this is 0 for the particle before and after, yes or no? And now for the lamina about A, what's the angular momentum? Look, this VCM, this length is A by 2. What's the angular momentum because of VCM about A? Let's say anti-clockwise negative. So minus MVCM into A by 2. Minus MVCM into A by 2. And then there is the ICM omega which is clockwise. There is a ICM omega which is clockwise. ICM for a square is 1/6 ma squared, is 1/6 ma squared. This is the angular momentum about a certain point for a body in general rigid body motion, general motion. That's how you compute angular momentum about a point, right? Leading to a VCM equal to A omega by 3. A VCM equal to A omega by 3. That's the nutshell of angular momentum. Are you okay with this? And then, finally, the fact that the collision is elastic. The fact that the collision is elastic. Can I just remove this because I have the final result for angular momentum mapped here. So now, the fact that the coefficient of restitution is 1. See, it becomes important. First of all, in E, we have what? The numerator is relative velocity of separation along the common normal divided by relative velocity of approach along the common normal. Now, when I take relative velocity of separation or relative velocity of approach, there is a velocity of particle which is clearly defined. But for the lamina, what velocity are you going to take? Because different points on the lamina have different velocity. So, what point would be looked into when the velocity of A? Yes, we'll have to look at the velocity of A along the common normal just before collision and velocity of A along the common normal just after collision. That's the important thing, right? In order to be able to write the expression for E, relative velocity of separation divided by relative velocity of approach for the particle, the velocities are like v by root 2 and v1 before and after along the common normal. For the lamina, what point would be the representative? The point where the collision occurs, the velocity of A along the common normal. Alright. Now, this is the center of mass with VCM. This is the center of mass with VCM, right? Just before collision, of course, the velocity of A is 0. Just after collision, if you have to compute the velocity of A, then you would superimpose the effect because of pure translation and pure rotation. Because of pure translation, the point A has a velocity VCM to the right, and because of pure rotation, you would imagine it to be hinged at the center of mass and possess an angular speed omega, in which case it's going to have a, if you imagine it to be in a state of pure rotation about the center of mass, then this would be this length into omega, this velocity would be the tangential velocity, this length into omega, yes or no? But this is like A root 2, so this is A by root 2, this is A by root 2. So this velocity would be A by root 2 into omega, into A by root 2 omega. But then for E, what would be the, so the net velocity of A would be the resultant of this VCM and this A omega by root 2 would be the net velocity. But what would be the velocity that would participate in E? It would be VCM plus A by root 2 cos 40 omega cos 45 degrees. This is 45 degrees. You can see this is 90 degrees, this is 45. So this is 45 degrees. Yes or no? So the velocity of A just after collision along the common normal direction is VCM plus A omega by root 2 cos 45 degrees. Yes or no? Which is A omega by 2. So just after collision, the relevant velocity of A is going to be VCM plus A omega by 2. That would be the velocity of A just after collision along the common normal direction. Is that fine with all of you? Huh? Alright. So now we are all set to be able to write the expression for E. Relative velocity of separation along the common normal divided by relative velocity of approach. Relative velocity of separation, that means if in the numerator I take lamina minus particle, then in the denominator I'll take particle minus lamina at A along the common normal, right? So then E is like a VCM plus A omega by 2 minus V1, relative velocity of separation along the common normal, right? Divided by relative velocity of approach along the common normal. Relative velocity of approach along the common normal means, now I'll take particle minus lamina. So V by root 2 minus 0. V by root 2 minus 0 for the denominator. That must be 1 because it's a perfectly elastic collision. Sorry? Yes? Yes. You can apply that, but then that leads to quadratic expressions which are not very happening. I mean, they'll only add to squalor. Fair enough? So then, well, these are constituent equations for the physics of the problem, and all that you need to do is very simple. I mean, you can write this A omega by 2. A omega you can write as 3 VCM, so this is 3 VCM by 2, and the V could be written in terms of VCM. The V could be written in terms of VCM, and you can solve for V1. It's easy to solve really. Again, V1, V, and the net velocity of the particle after collision is going to be root V1 squared plus V by root 2 whole squared, etc. So everything you know in terms of V. You know in terms of V. Ordinary situation of string constraints which we elaborately dealt with. We have this system here with this mass A being given, let's say, a velocity VA to the right, right, And all that you need to do is along the string assign velocities. So along the string, the velocity of A is like V cos theta. This is another node 0. This is a node 0. This point will have the same velocity as B, VB. This point will have the same velocity as B, VB. And then 0, right? And then you go from here to there like we done beginning of class 11. So then we go from here to there. This is like 0 minus V cos theta. And then 0 minus 0 for this. And then from here to here, we have like a minus VB minus 0 for this segment. And for this segment, this is VB upwards. We have 0 minus VB. And this must add up to 0. That's the string constraint that we learned, isn't it? That's what we learned in string constraint. It's all wiped off, yeah? I hope. It's wiped off, no? Okay. So then VB is V by 2 cos theta. VB is V by 2 cos theta, where cos theta is x by root h squared plus x squared. That's cos theta. That's the velocity of V. Right? I mean, we did ample stuff of this kind beginning of class 11, so I expect enough comfort level. Now, this whole surface is smooth. This is smooth. There is a collision in this direction, and that means essentially this is 10 meters per second like this, digging into the body. And the radial direction is the common normal direction. The impact direction is the radial direction, the common normal direction, right? Realize that this is r by 2, this is r. So then sine of this angle is half. Sine of this angle is half, so this angle must be 30 degrees. This angle must be 30 degrees. The initial 10 meters per second, could be resolved as 10 cos 30 degrees along the common normal direction, participating in collision, right? 10 cos 30 degrees means 5 root 3 meters per second. 10 cos 30 degrees is 5 root 3 meters per second, and 10 sine 30 degrees, which is 5 meters per second, which is tangential direction. Okay. What would change after collision, this or this? This, because it's smooth. We'll assume that the collision is on smooth surfaces, so this is not going to change for the particle after collision, whereas this will change. Now, the particle exerts on the sphere, impulsive force in this direction, exerts an impulse in this direction on the sphere, yes or no? Which passes through the center of the sphere. So, does this force produce any torque about O? There is no torque produced about O. If there is no torque produced about O, does it add to any alpha? Is there any build-up of omega? No. So, after collision, there is no omega build-up. So, omega is 0 for sure before and after collision. Do you understand this? There is no omega. Omega is 0. And there is no frictional force that could have, produced a torque about O. So, omega for sure is 0 after collision. On the sphere, the only force that acts, of course, there is an impulse from the ground, but all of them pass through the center. No force is eccentric, and therefore results in no torque about O, no omega buildup, right? So omega for sure is 0. That's a right away implication of things here. Confusion? Can you take torque about every point? पर यहाँ पे when a body is at rest, what's the instantaneous center? All points are instantaneous centers, and therefore no point is an instantaneous center, right? So when a body is at rest, then the sanguine point is the center of mass about which you want to, right? Now, so the particle exerts on the sphere. Is it a sphere or a disk? Does not matter though. Whatever. Exerts on this body an impulse J in the common normal direction. This is out of the colliding effect. Out of the colliding effect, an impulse J acts on it. Now, this J has a vertical component which is managed by the extra thrust that the ground exerts, preventing no change in momentum in the vertical direction. Yes or no? Right? A vertical component is countered by extra normal force from the ground, creating no net effect in the vertical direction. Are you there with me? However, the horizontal component of J will produce on the center of the sphere a velocity V. The horizontal component, that means J cos 30 degrees. J cos 30 degrees must be, the mass of this is M, must be M into V. J cos 30 degrees is the horizontal impulse acting on this, producing change in linear momentum in the horizontal direction, which is mv on the sphere. Right? Is there any confusion so far? No, no? Now, the particle side of the story. This is the sphere side of the story, the particle side of the story. The particle will be acted upon by an equal and opposite impulse like this. Would be acted upon by an equal and opposite impulse like this. Right? The particle exerts on the sphere an impulse like this. The sphere will exert on the particle an impulse like this. Radially outwards. Yeah. Good law. Right? Now, what does this impulse do? This impulse will alter this velocity. Right? Now, instead of being 5 root 3, it will become some V1. Let's say it will become some V1. So, just after collision, because of J acting like this, the 5 root 2 gets, becomes V1. The 5 root 3 for the particle becomes V1. And what happens to this 5? Nothing. It maintains status. So, for the particle, just after collision, this 5 is 5. Right? Now, listen to me. In a perfectly inelastic collision, where have I crossed those borders yet? In a perfectly inelastic collision, the important thing is this is an oblique inelastic collision in which relative velocity of separation along the common normal must be 0. Realize that? Relative velocity of separation along the common normal is 0. It doesn't mean that the particle will necessarily have to stick to the mother body. It's just that along the common normal, their relative velocity must be 0 in a perfectly inelastic collision. Yes or no? Right? Are you there with me? Right? If it was a head-on collision, it will become integral with the body and move commensurate. But in an oblique collision, which is what it is, its relative velocity of separation along the common normal, which must go into oblivion. Right? Good. Now, let me apply the impulse equation on the particle. The particle is subject to an impulse like this. The impulse on the particle in this direction would be final linear momentum of the particle in this direction minus initial linear momentum of the particle in this direction. Yes or no? The particle is of mass m by 10. Particle is of mass m by 10. So, the linear impulse in this direction on the particle is going to be final angular momentum in this direction, which is minus m by 10 into v1 minus initial angular momentum and the initial linear momentum in this direction, right? Right? Impulse in this direction means final linear momentum in this direction minus Initial linear momentum in this direction. That's what impulse in a given direction means. Yes or no? Why are you giving me dirty stares? Say yes or no. Right? So final linear momentum in this direction is minus m by 10 into v1 minus initial linear momentum in this direction is minus m by 10 into 5 root 3, right? So minus m by 10 into 5 root 3. Final linear momentum along J minus initial linear momentum along J, that's J, right? Which is like m by 10 into 5 root 3 minus v1. Sounds all right? So that's the sphere side of the story. This is the particle side of the story. And now the nature of collision. The last part of the physics is documenting the nature of collision, which is E equal to 0. E equal to 0 would mean relative velocity of separation along the common normal must be 0, right? That means along the common normal, the velocity of this is v1 after collision. Separation means after collision. The velocity of this along the common normal is v1 after collision minus velocity of the sphere along the common normal is v cos 30 degrees. And by the way, the sphere is in a state of pure translation. So the velocity of this point of collision is also v. The point on the sphere will share a common velocity with the center of mass. So this point of collision has a velocity common with the sphere v to the right, because there is no omega. It's a state of pure translation that is generated because of this collision, right? So the velocity of this point of collision in this direction is going to be v cos 30 degrees for the sphere along the common normal. So v1 minus v cos 30 degrees, which is relative velocity of separation along the common normal, and that must be, this is the sum total of the physics involved in the situation. You can eliminate J by this and then use this and this to solve and B. Does it make sense to all of you? So here we have a can of mass capital M plus small m and a man of mass capital M holding a ball of mass small m. That's what. So the total mass to begin with is capital M of the man and small m of the ball. The system is in equilibrium, obviously. No acceleration, nothing. Now, the moment this fellow releases the ball, this becomes capital M. The ball will begin to fall down with a velocity, with an acceleration g and initial velocity 0, right? The ball will begin to fall with an acceleration g. It's now free to fall under gravity, right? And this mass now becomes capital M plus small m, and this mass is capital M. So it will have a downward acceleration. It will have a downward acceleration A, right? And then to compute the downward acceleration of the can, all that you need to do is, this tension is T. Now, as is regular, m plus m into g minus T is m plus m into A, and for this, T minus mg is capital M into A. Add these two, so you have like 2m plus, rather mg, small mg is small m plus 2m into A. So A is known, the acceleration of the can downwards, is like mg by small m plus 2 times capital M. So the acceleration of this is known, the acceleration of this is known, right? Their initial relative velocity is 0, their relative acceleration is g minus A. Their relative acceleration is g minus A, yes or no? Relative acceleration of the ball with respect to the can is g minus A. Initial relative velocity is 0 because both start with 0 velocity, and the relative distance to cover is h. The relative distance to cover is h, right? So h must be half of relative acceleration into t square. No? Are you there with me on this? So, A rel is g minus A is known, relative initial velocity is 0, relative displacement is h, and this will give you t, time in which the ball hits the can. No confusion. Alright, so here we have a system of two identical masses connected by a light rod, inextensible light rod on a horizontal frictionless surface. And this end is given an impulse V0. This end B is given an impulse V0. Because of this impulse, general rigid body motion results. For the system, general rigid body motion results. The center of mass of this two particle system is halfway down, midpoint. So the center of mass of the system, because of this, just after the impact, just after the impulse, would develop a VCM. No. And you're giving it a velocity like this, you can notionally imagine that there would be an omega developed this way, there would be a omega developed this way. Right? So far so good, right? Now, what's going to be omega? The velocity of this is 0, right? The velocity of this is 0. So this is a rigid body, the velocity of this end is V0 perpendicular, this length is L. So omega developed is V0 by L. Omega developed is V0 by L, yes or no? And then this length is L by 2. Realize that the velocity of this end V0 is because this has a VCM in this direction, and then because of pure rotation it's L by 2 omega. See, this V0 is the result of a VCM plus, because of pure rotation about the center of mass, a tangential velocity L by 2 omega. Yes or no? But L omega is V0. L omega is V0, so this is V0 by 2. So VCM we know is V0 by, VCM we know is V0 by 2. Right? Okay. Once we have this data in place, life becomes easy, because one thing, the center of mass will continue to move with V0 by 2, and the omega V0 by L will be maintained. So this would be in a state of general motion, translating because of VCM and rotating because of omega, right? So after a while, from its reference position, it would have, the rod would have got tilted by an angle theta. It would have got tilted by an angle theta, where theta is some omega t, where theta would be omega t. The extent of tilt will be measured by omega. Theta would be omega t, it would have got tilted. So after a while, let's say the orientation of this would have obviously translated forward too. In addition, it would have got tilted, A would have come here, B would have come here, and the tilt theta from the initial vertical would have been omega t. Omega is known to us? No? Right? Now at this juncture, look at the velocity of P. Look at this velocity of P. Realize that the center of mass maintains a velocity V0 by 2, and the omega is V0 by L, right? So the point B at this juncture, the point B has a velocity which it shares with the center of mass, which is V0 by 2, and then imagine it to be in a state of pure rotation about the center of mass. It will have a velocity perpendicular to this If you imagine it to be in a state of pure rotation about the center of mass, it will have a velocity which is like L by 2 omega, which will be L by 2 omega, yes or no? Evidently, if this makes an angle theta with the vertical, a perpendicular to it, which is this, will make an angle theta with the horizontal. Right? Now, L omega is V naught. So, L omega by 2 is like a V naught by 2. It's like a V naught by 2. So, the resultant velocity of B at this point is the resultant of this V naught by 2 and this V naught by 2 at an angle theta at an intermediate instant. Isn't it? So, for the point B, we have like a V naught by 2. At this juncture, at an instant of time t, when it would have described an angle theta with respect to the initial reference. Evidently, then the velocity of v from parallel this square plus twice this into cos theta, right? 2 into v naught by 2 whole square plus 2 into v naught by 2 whole square into cos theta, which is v naught by 2 into root 2 into 1 plus cos theta, which is 2 cos square theta by 2, which is v naught cos theta by 2, which is v naught cos theta by 2, right? Now, at this point then, B has a velocity Vb, which is v naught cos theta by 2. In a small time dt, the distance covered, in a small time dt from this point, the distance covered would be Vb dt. In a small time dt, the distance covered would be Vb dt, right? The total distance covered in time t equal to 0 to some instant of time t which is given in the problem, right, will be this, where Vb is v naught cos theta by 2 dt, where theta you can write as omega t, theta you can write as omega t and integrate from 0 to some time t which is given in the problem. That will be the total distance. Yes or no? Theta could be written as omega t, omega v naught is v naught by L, and you can integrate with respect to t and then plug in limits 0 to t, the t that is given in the problem. Supply the limits, that will give you the total distance covered by the point B in the proposed time. How about it? Does it make sense to all? Alright, so falling from a height h, its velocity becomes horizontal, root 2 gh, right? Zero angular velocity because it's saying that it slips. That means there was not enough traction for any omega to get built up during the descent, right? So it falls onto the plank which has enough friction in it, and it has a horizontal velocity v naught. So then, look at this point. At this juncture, this point has a rightward velocity v naught. So the plank will exert on this mass small m. It's a sphere or a cylinder? A cylinder. On this cylinder, it exerts a frictional force mu mg. The cylinder in turn will exert an equal and opposite force on capital M, mu mg. So then, the acceleration of the plank is going to be mu mg by capital M. That's going to be the acceleration of the plank, rightwards, because the cylinder exerts on the plank an equal and opposite frictional force mu mg to the right, producing an acceleration mu mg by capital M, right? Now, what would this frictional force do? It will retard the center of mass, and it's going to produce a clockwise torque, which will produce a clockwise alpha and therefore a clockwise omega, right? So this keeps getting killed and omega keeps getting built, right? After a while, well before it reaches the end of the cylinder, since there is enough friction, you would expect rolling conditions to have got generated on this, when the velocity of this point of contact of the cylinder becomes the same as the velocity of the plank, right? The velocity of the plank at any given instant of time t is like ap into t would be the velocity of the plank, right? When rolling conditions are produced, there is a VCM and there is a omega. Let's say this is t equal to 0, this is t equal to t seconds. Evidently, the retardation on this because of mu mg is a mu g. So between this state and this state, v equal to u plus at if I apply, I get like a VCM equal to initial velocity v naught minus mu gt, right? The angular acceleration alpha is mu mg into r. Is the torque about O? So angular acceleration produced is mu mg into r divided by I about the center of mass, which is half mr squared, which is 2 mu g by r. This 2 mu g by r. So then at this juncture, at t seconds later, the omega becomes alpha t. Omega is omega naught plus alpha t. So omega becomes alpha t, which is like 2 mu gt by r, right? Now, what would be the condition? What would be the velocity of the plank at this instant of time? ap into t would be the velocity of the plank. That would be the velocity of the plank. Now, if rolling has commenced here, then what would be the required condition for rolling to have taken place? Velocity of the point of contact of the cylinder must be equal to the velocity of the plank. Yes or no? There must be no relative motion at the point of contact. That's the condition for rolling. It's not like VCM is r omega at this juncture, right? So realize that for the cylinder, the velocity of the point of contact is VCM because of pure translation, and because of pure rotation, it's r omega, right? And that must be equal to Vp. That must be equal to Vp. Where VCM you can write as V naught minus mu gt, and r omega you can write as 2 mu gt. R omega you can write as 2 mu gt. Oh, I'm sorry, this is like this. Yes, VCM minus r omega. I stand corrected. This is r omega like this, VCM like this. So this is VCM minus r omega. So minus 2 mu gt, and that must be Vp, which is velocity of the plank at that instant. So that's like a mu mgt by capital M. So solve for t straight away from here. You know the time when this happens. And once this starts, rolling starts, there is a VCM here and there is a omega there, right? From that point onwards, what's going to happen? First of all, do you realize that it's given that mu is large, which means what is ensured is that rolling conditions will take place in a short time, good enough to have taken place within this span, within the length of the platform, right? So before leaving the platform, it would have already acquired a rolling state, because it's given that mu is large. If mu is large, time taken for rolling would be less, and it's less enough to have been acquired well before the cylinder reaches this end of the plank, right? So once rolling commences, this has acquired a VCM, this has acquired a omega, and this would have acquired a VP. What according to you would happen from this point onwards to the plank, the VCM, the omega and VP? What would happen? It will remain the same. It will remain the same. So it will leave the plank where even though it would have acquired a rolling condition here, the same kinematic status would be maintained by the cylinder, by the plank from this point onwards. So when it leaves the plank, it would leave it in this state, The VP of the plank would be what it got at the instant rolling commenced, and when it bids farewell here, it would have the same state as the rolling state. Got me? A particle of mass small m is moving with a velocity u1 equal to 3I plus 2j, and it collides with a stationary body of mass capital M. That means for this body, its initial velocity for this body is 0. After collision, small m has a velocity v1 which is minus 2I plus j, And if you have to compute the final velocity of this, which is v2, then all that you need to do is apply conservation of linear momentum. So then we have like mu1 3I plus 2j plus capital mu2, which is 0. That must be mv1 plus capital M v2. v2 is what we are seeking in the problem. So mv2 then is m into 5I plus j, and it's given small m by capital M is 1 by 13. So then v2, the final velocity of the bigger block, is 1 by 13 5I plus j meters per second, right? So far so good, not an issue. Coefficient of restitution. For coefficient of restitution, you will have to take the relative velocity of separation along the common normal. That means v2 minus v1 along the common normal direction divided by u1 minus u2 along the common normal direction. But the point is, what is the common normal direction? Point is, what is the common normal direction? After all, let's say if n cap is the vector along the common normal, if n cap is the vector along the common normal, then essentially, then the coefficient of restitution would be v2 minus v1 relative velocity of separation dot n cap divided by relative velocity of approach u1 minus u2 dot n cap, right? What then is n cap? What's the common normal direction? Look, there is change in linear momentum of small m, for example, right? The change in linear momentum for small m is m into v1 minus u1. This is the change in linear momentum of small m. This is the change in linear momentum for small m. That means on small m, this must be the direction of the impulse acting on small m. Yes or no? This must have been the direction of the impulse. Impulse on small m that capital M exerts is m into v1 minus u1. right? But the impulse acts in the common normal direction. The impulse in a collision will act in a common normal direction, yes or no? That means the direction of J is the common normal direction. This is the impulse acting on change in linear momentum of small m. Will be the impulse acting on small m, but the impulse will act only along the common normal direction. Are you there with me? That means a unit vector along J would be n cap. A unit vector along J would be n cap. Are you fine with this? Sorry? No. What would be the? No, but we don't know. It's an oblique collision. Okay, you mean it will move in this direction. So, suppose this is how it was, right? And there was U1 like this acting on it, right? And this is capital M. You want to say that now this U1 would have a component like this and would have a component like this along the common normal direction and perpendicular to the common normal direction. So then the direction of motion of M would be this, which would be the direction of V2, isn't it? Which is the same thing, which will be the same thing. I agree with you. I mean, realize that I could have also taken, which is no different, which would be the same thing, because the impulse acting on capital M would be equal and opposite to the impulse acting on small m. So the normal direction computed from the impulse on capital M or the impulse on small m would essentially be the same. They would just be in opposite direction. So instead of dot n cap, you might have a minus n cap here and a minus n cap here, which would lead to the same dot products essentially. So it will not make any difference, right? So what he's saying is, I can take the impulse on capital M, in which case it would be the same as the direction of V2. Fair enough. This unit vector in this direction would be n cap. Unit vector along V2 would be n cap, because the change in linear momentum on M, capital M, is m into V2, which is the direction of the impulse acting and which therefore must be the direction of the common normal. Has to be the same. I mean, if you use capital M and you get J, and if you use small m, you will get minus J. That means instead of n cap, you will have a minus n cap here and a minus n cap there. Then you will have to use both in the numerator and denominator the same n cap. The minus will get cancelled, it will make no difference, right? So all that you need to do is, and instead of n cap, you can use J also. I mean, n cap is what? J by mod J? J by mod J, but mod J would get cancelled. See, n cap is J by mod J. It does not matter. Mod J would get cancelled from numerator and denominator. So it will be this dot J divided by this dot J. J or minus J. It's going to give me the same result, isn't it? Because they exert equal and opposite impulses on each other. It's going to be the same direction. Fair enough? Alright, we have a system of two masses, m1 and m2, resting on a rough surface, coefficient of friction mu. Initially the spring is unstretched. At that instant, a constant horizontal force F acts on it. We need to find that minimum value of F, for which this just about begins to slide on the surface. Now, when I talk of a minimum F, means the F is not building velocity. F is not building velocity. It means essentially what really transpires is that after a while, when m1 is on the verge of sliding, the spring would have got elongated by an amount x, exerting a force kx on this mass, which just about becomes equal to mu m1g x, right? Mu m1g, right? Such should be x. Now, between this state and the state in which the spring has got elongated by an amount x, let's apply work energy theorem. In between this state and the final state, there is no change in kinetic energy. That would be minimum F. A value of larger than what we calculate will not only cause this to slide, but will also build kinetic energy in the system. But when we are saying minimum F, means the F is small enough to not add kinetic energy to the system. All that it's doing is, in a quasi-static manner, it's elongating the spring so that it elongates to the extent that it's able to just about cause this mass m1 to slide on the ground. So between this state and the state in which the spring has got elongated by an amount x, that means m2 would have moved to the right by an amount x. So what's the work done by F? F into x. So in order to come from this point to this point, the spring would have got elongated by an amount x. The mass m2 would have moved to the right by an amount x. The work done by F must have been fx2, fx, right? The spring, having got stretched by x, would have work done by the spring would be negative of the change in elastic potential energy of the spring, that is minus half kx square. And then, since m2 is actually sliding on the ground, it's subject to frictional force. Static friction would have reached mu m2g. So work done by friction on m2 would have been minus mu m2g into x. That must have been the work done by friction. And that must be change in kinetic energy of the system, which is 0 for minimum F. Change in work energy theorem, this must have been 0. So which means F minus kx minus mu m2g is 0, but kx, F minus kx by 2. But kx must have been mu m1g for this instance, so that m1 could just slide on the ground. Kx must have been mu m1g, how about it? So plug kx equal to mu m1g, kx equal to mu m1g, F becomes mu g into m1 by 2 plus m2. That's the minimum F. F larger than this, by the time an elongation x is reached, would have also produced a velocity in this mass. Any F larger than this. So this F would not add to kinetic energy, but would just produce enough elongation for sliding to just about commence for m1. Right? Got me? Look. When this particle is hurled with a velocity u making an angle theta, then it's subject to an acceleration g cos theta in this direction and a g sin theta in this direction. When you apply a force F on this, now it has like mg cos theta like this, or normal reaction R like this, and a mg sin theta like this. Right? Now the acceleration of the block in this direction is 0. So this component of the acceleration of the block is 0. No matter what F, this component of the acceleration is 0. Now what we are seeking is the value of F so that the acceleration of the particle with respect to the block is g cos theta, is g cos perpendicular to the plane. Is g cos theta perpendicular to the plane. You are seeking a value of F so that the acceleration of the particle with respect to the block is g cos theta perpendicular to the plane. Right? Now, that means parallel to the plane their accelerations must be 0. Parallel to the plane their relative accelerations must be 0, yes or no? Parallel to the plane, relative acceleration must be 0. Right? Now, acceleration of this parallel to the plane is g sin theta. So, the acceleration of this parallel to the plane, let's say, is A parallel. This minus this must be 0. A parallel is the acceleration of this parallel to the plane. That must be 0. Relative acceleration parallel to the plane is what? Acceleration of this particle parallel to the plane minus acceleration of the block parallel to the plane. Let me take the acceleration of the block parallel to the plane as a parallel. So this must be 0. So the acceleration of the block, this is for the block. That means a parallel for the block must be g sine theta. Yes or no? That means the acceleration of the block in this direction must be g sine theta. When can that happen? When f is 0, isn't it? The acceleration of the block in this direction must be g sine theta, and that can happen when f is 0. That means now, when f is 0, the acceleration of the block in this direction is 0. So the relative acceleration in this direction is g cos theta, and in this direction, the relative acceleration is 0 because this has g sine theta and this also has g sine theta. Right? So f must be 0. F must be 0 for sure, right? Now, if the particle starts at the corner, strikes at the corner A of the block when the speed with respect to the block is minimum, that means this point must be A. When it strikes A, this is u cos theta where it started, parallel to the plane, and see u cos theta parallel to the plane and u sin theta perpendicular to the plane. And this point, at this point, its vertical velocity becomes 0. This is the point A, and this must be the height h that we are seeking. This must be the height h that we are seeking, isn't it? That's what we are seeking. We are seeking h, the side when the velocity is minimum. That can happen when it's parallel to the inclined plane, right? So then, between this point and this point, realize that acceleration in this direction is g cos theta, in this direction is g sin theta. So applying v squared minus u squared is 2as in this direction. In this direction, we have 0 squared minus u sin theta squared equals 2 times minus g cos theta into h, displacement in the h direction. I mean writing v squared minus u squared perpendicular to the plane. V squared minus u squared perpendicular to the plane. Yes or no? H is then known. Fair enough. So you know this h. Alright. So the system is hinged at C. This is a disc, right? It's a disc which is hinged at C. It's in a vertical plane. And when it's released, then there is mg acting like this. There is mg acting through O, which will produce about C, or torque in this sense, which will produce an alpha in this sense. Yes or no? So there is an alpha that's going to be produced. So the alpha that's going to be produced is like a mg into r by root 2. That's the torque about C divided by I about C. I about C is I about O plus m into this squared, parallel axis theorem. So I about C is half mr squared plus m into r by root 2 squared. So that's alpha. That's alpha. mr squared, which is g by r root 2. G by r root 2 is the angular acceleration about C just after release. Clear? Now, if the reaction at C is R, then this is the center of mass. The center of mass will have an acceleration ACM. The center of mass will have an acceleration ACM, which is like mg minus r must be MACM. mg minus r must be MACM, yes or no? R is the reaction. right? I need to compute R. Now what's ACM? Realize that this point at this, it's hinged about C. So ACM must be R by root 2 into alpha, isn't it? ACM must be R by root 2 into alpha, angular acceleration alpha, yes or no? So ACM is R by C, it's in a state of pure rotation about C. So A of this point would be this distance into angular acceleration alpha, right? Tangential acceleration. So ACM is R by root 2 into alpha. So R alpha is G by root 2, R alpha is G by root 2. So this becomes like a G by 2, ACM becomes G by 2. So we have R equals mg by, that's a reaction.